Welcome back to Sciencing Around, and now we are seeing the part 2 of the wave optics. Last time we did the basics, and now let's do the main thing, that is Young's double slit experiment. Now first, what did Mr. Young do? That is, he just kept the slit here. Now as you can see, here is a slit having just one very small hole, S. And after that slit, the light just passes through it, and as I said, light runs as spherical waves, so I have drawn it one-dimensionally. Goes like this. There are again a slit which has two more very small slits, and then light again passes through it. So how does the light passes? Let's see with the diagram. Not this one. I've got some other one for you. This one. Is it okay for you? So okay. Here's the light passing. You can see here. Here's the two those small slits having the distance d. The light gets deflected from its straight line and gets down somewhere here at point P, and D is very small than this capital E, which is the distance. The angle made by this change of the side of the angle is change of the side of the traveling of light is theta, and distance between P and O is yn. That's all about the Young's double slit experiment. Let's see what it says. Alright, let P be any point located on the screen. Yeah, this point, right? The optical path difference between the S2P and S1P equals to S2P minus S1P equals to d sine theta. But since the capital E is much greater than small d, also capital E is much greater than the distance, we should say yn, then what is P? P is nothing but d times yn upon d. That is small d into yn upon capital D is the point P. And now what is sine theta? We know now, since d is much greater, sine theta is approximately equal to tan theta. Tan theta is opposite upon adjacent, which is yn upon d. That is nothing but tan theta. And now let's learn about the maximas and minimas, which is here, right? Now if maxima is formed at P, then P equals to the nth multiple of lambda, where n can be between 0, 1, 2 and all that. That is dy upon d, that is small d into yn, that is the width upon capital D, equals to n times lambda, because P is this. And by rearranging yn equals to n lambda d by d. If minima is to be formed at P, now if maxima is formed, that is means the maximum distance, and now the minimum distance is to be formed at P equals to n minus half multiple of lambda, that is n minus half multiple of lambda, n is again 0, 1, 2, 3, and thus y equals to n minus 1 by 2 lambda capital D upon small d. Since right here like this, just it's not n, it's n minus 1 by 2. Now what is fringe width? The distance between two successive maximas and minimas. As the definition says, the intensity, or I must say the fringe width, is mostly denoted by beta, which is lambda times capital D upon small d. And intensity at bright fringe is 4 times I naught. You have to learn this thing. At any bright fringe, as you can see in the Young's double slit experiment, fringes are formed bright, dark, like that. So at any bright fringe, intensity is 4 times the initial intensity, or 4 times the actual intensity of light. And at dark fringe, of course it's a dark, so intensity should be 0. Now as I said that the resultant intensity is this thing, I naught plus 2 root I naught cos theta, that is under root of I naught plus under root of I naught the whole square, where the angle between them is phi, so cos phi. So by resultant vectors and all that thing, we did this thing, and thus I equals to 4 I naught cos square phi by 2. Important formula, guys. Now some important points let us learn. I hope you can see this. If one of the slits is covered by fingers, if one of the slits is covered, then the fringes disappear. That's so obvious, because of 2 slits the light is actually deflected. So if we cover one of those slits, then each and everything would just disappear. That's quite obvious. The screen is moved away from the screen, or if the screen is moved away from the screen, the fringes separation increases. That is, if these two are increased or these two are just taken away from each other, this distance increases. Now, if white light is used, central fringe is white, nearest to central fringe is blue, and the farthest is red, because red has VIBGYOR, right? If source slit is moved nearer to double slits, fringes separation is unaffected, but intensity does increase. That is, if the source slit is moved nearer to the double slits, that is, if this slit is moved toward this thing, the fringes separation is of course unaffected, but the intensity does increases. That's true. And if width of S is more than the lambda d dash upon d, fringe pattern disappears. That is, if width of S, that is, of course, if this width is greater, this should be very small. Now let's get down to the last page of wave optics. Now, what is angular fringe width? What is theta? Theta is approximately equals to y by d. Now what is theta? Theta is the angle I told you, and y by d, you know what's y, you know what's d. I did tell you. So change in theta would be dy upon the capital D, and we know that change in y equals to beta. This is the fringe width, and thus d theta equals to beta upon capital D. Thus beta equals to d lambda by 2d, as you can see by the whole fucking derivation. So delta theta equals to lambda upon 2d. That's quite obvious, because we know delta theta equals to delta y upon d. We know delta y equals to beta. You know what is beta? I told you the formula. So delta theta equals to lambda upon 2d, where delta theta is angular fringe width. So change in fringes due to change in medium. Now, if between the slits we just take some another medium of some another refractive index for lambda wavelength, then beta is of course d lambda by 2d. If the medium becomes nu, lambda dash is the changed wavelength, then lambda dash would become lambda upon nu. That's quite obvious, because the lambda varies inversely with the refractive index. So beta dash equals to d lambda upon 2 nu d, or we can say d upon 2d into lambda by nu. And thus the change in fringe width would be minus of d upon d, that is minus of capital D upon small d, into lambda into delta d dash, if slit separation is varied from d to d dash, that is from this d to some other value, right? Fringe shift due to thin film. Now, if a transparent sheet of refractive index nu and thickness t is introduced to the path of the interfering light, the optical path difference, or delta x dash, equals to 2y d by d times I times nu minus 1t. I don't know how this derivation came from the sky, from the space, from the Mars, I don't know, but it's the formula. Now we know y equals to nu minus 1 dt upon 2d, because according to this formula, and there will be no change in fringe width. I think that was all for now. I think we completed with those wave optics. Next lecture, I don't know what would I take, something which is quite interesting. This video is ended here, so thank you for watching. If you like this video, please press that like button and do subscribe my channel, and please comment how did you like this video and what should I improve. So thanks guys, see you soon, happy sciencing.